So we have helium gas. It flows through a well-insulated nozzle at steady state. So what does a nozzle look like? Well, it'll be a section with reducing cross-sectional area. We're not going to study at this point compressible flow and velocities greater than the speed of sound. That would be studied in chapter 9. But this is a very simple subsonic nozzle. And so for our flow, it's going to just have the area at the inlet state 1 compared to the area at the exit state 2 is going to be lower at state 2. It's going to be smaller cross-sectional area, and hence it'll speed up. Okay. The inlet is at a given pressure, P1 of 320 kilopascal, temperature of 550 Kelvin, and a velocity or speed of 45 meters per second. Whenever they give you this velocity or speed, what you need to do is think about kinetic energy effects. That's a key. Don't neglect kinetic energy effects. Okay, at the exit, the pressure is given P2 of 270 kPa, and the temperature T2 is 520 Kelvin. The area at the exit is also given to be 0.0008 meters squared. Okay, they did not give us A1, but they give us A2. Using the ideal gas model, when you see that, three things come on. You think of PV is equal to RT for that gas of interest. This time it's helium, and that is a very good ideal gas typically. And then you also have that U is a function of temperature only and H is a function of temperature only. So the internal energy is a function of temperature only and the enthalpy is a function of temperature only. Okay. They also give us a constant value of K. When you see a constant value of K, basically you're going to treat the gases as having constant specific heats. So if you're given K of 1.667, which is a very typical value, then for a monoatomic gas, then you know that you can use equation 3.47 out of chapter 3 of our textbook to get the specific heat constant volume and the specific heat constant pressure, knowing the gas constant for this gas of interest, helium. And so the values are the gas constant divided by K minus 1, or K times the gas constant divided by K minus 1. All right, and then as a reminder, this R for the gas of interest is our universal gas constant divided by the molar mass. And the molar mass of helium, we can look up, it comes in at 4.003. So the molar mass of helium, 4.003 kilogram per kilomole. That's a lot of background material, but all this is sort of prerequisite. It's out of the previous chapters. We're finally getting into chapter 4, and this deals with the conservation of energy and control volume analysis. So let's continue to look at our problem. We have neglect potential energy effects. So the elevation difference between the inlet and outlet is negligible, so we neglect potential energy effects. And you're asked to solve for the exit velocity and the mass flow rate. Well, how do we solve for the exit velocity and mass flow rate? Well, this is in the chapter dealing with a control volume analysis, and we're doing a mass balance as well as an energy balance using this analysis technique of a control volume. So what we're going to do is introduce a control volume. The control volume basically has an inlet here at state 1 where the flow is coming across, and then along the edges there's no outflow along the walls of the nozzle, and there's no heat transfer into the system, nor is there shaft power out of the system for a nozzle. Those are our standard assumptions. They do say it's well insulated, so that emphasizes that there is no Q dot for this nozzle. And by definition, what a nozzle is just there's no W dot, there's no shaft in or out. If they said it was a turbine or a pump or a compressor, well, then we have shaft power in or out. Then you have flow across the exit. Okay, so if this is my control volume, I think of having two things. I have the conservation of mass. So the mass balance would be something like the rate of change of the mass in the control volume with respect to time. It can go up if I'm adding due to inflow. And for this problem, we said the only inflow is state 1, mdot 1 coming in, minus mdot 2 going out. So one inflow, one outflow. It said it's steady state, hence there's no accumulation or depletion of mass in the control volume. And so we find from the mass balance that mdot 1 is equal to mdot 2. We just forget the subscripts. We just say there's one mass flow rate through the whole system and it's constant. Okay, let's now go to the energy balance. So we say the rate of change of energy in the control volume. Well, how can the energy in the control volume be realized? You can expand that into three terms. We have the internal energy in the control volume, the kinetic energy in the control volume, and the potential energy in the control volume. Let me just write it like that for now. You're going to see that's all zero. Why is that all zero? Because it's steady state. Steady state. Okay, but let's continue this equation for the general first law for a control volume. We have the Q dot coming in minus the W dot going out. Again, we just talked about those for this problem. It's well insulated, and because it's a nozzle, there's no shaft power in or out, just by what it is. Then we have our mass flow rate. Now, we typically put mass flow rate in, bringing with it its enthalpy in, and kinetic energy in, and potential energy in. So we could put mdot 1, and then all these H1, KE1, PE1, and then we'd put minus mdot 2, H2, let me not put too many subscripts there, plus kinetic energy at state 2 plus potential energy at state 2. Okay, but we already talked about these mdots being the same, so often you just drop those subscripts. And we're told from the problem statement the change in potential energy or potential energy effects are negligible. And so the first law for a control volume applied to this well-insulated nozzle at steady state flow boils down to 0 on the right-hand side, equal to mdot. Then you have the enthalpy coming in minus the enthalpy exiting, plus kinetic energy coming in minus kinetic energy exiting. Now, a nozzle is one of these devices where the purpose is to bring it out at high speed. You know, the nozzle, you want V2 to be high. So in typical nozzle analysis, we don't neglect kinetic energy effects. We want to include it. All right. So if we're using constant specific heats, then we can replace first of all, we can divide each side of the equation by mdot and get rid of that. And then we can rewrite this as the kinetic energy exiting at state 2 because we're looking to get the velocity at the exit. And we know that the kinetic energy is related to the velocity because the kinetic energy at state 2 is 1/2 V2 squared. So if we can get the exiting kinetic energy, we can get the velocity. So that's our approach. So that's equal to KE1. Then we're going to have plus H1 minus H2. Okay. Well, I need more room and I don't want to go slide this down, so let me kind of write it like this. Come up here. And so the 1/2 V2 squared is equal to 1/2 V1 squared. And then you can replace this change in enthalpy by C sub P T1 minus T2. Okay. Now we can have the velocity at 2 is equal to the velocity at 1 squared plus 2 times c sub p times t1 minus t2, all of that square root. Now, the only thing you have to be careful of are units. And so I'm going to put a little extra room in here underneath the square root. And I'm going to remind you that 1,000 meters squared per second squared is precisely 1 kilojoule per kilogram as a unit conversion factor. So that you look at the units on c sub p, and you find that you need that unit conversion. So let's go ahead and substitute some numbers. So it comes in at velocity v1 of 45 meters per second. I know that's going to be in there. I'm going to run out of space. I'm going to not put those units explicitly in there. We'll have plus, I'm going to put 2,000, then c sub p. Well, we do a little bit of work. We know the molar mass. We know r bar. We get r. C sub p is this k times r divided by k minus 1. For this problem, c sub p boils down to 5.1924 kilojoules per kilogram Kelvin. I didn't leave, that doesn't look good. 5.1924. Okay, so 5.1924. And then we have our two temperatures coming in at 550. Going out at 520. We find that V2 is 560 meters per second. Box it, and that's our answer for part A. And there it is, 560. Very good. How about the mass flow rate? Well, the mass flow rate would be our volumetric flow rate, AV, at either the inlet state 1 or the outlet state 2, because we're given the area at 2. We'll say the area, the volumetric flow rate at 2, and then we're going to divide by the specific volume at state 2. Well, how do we find the specific volume at state 2? Just come back here and use the ideal gas equation. V2 is equal to the R T2 divided by P2. We've done that a few times. Let me just give you the result for that specific volume. It turns out to be 4.0000 meter cubed per kilogram for this problem. And then you had the area 2, 0.0008. And then you had the velocity at 2, we just calculated. And so I'm running out of room, but mdot turns out to be 0.112 kilograms per second. That's the answer for part B. A couple things to point out. Most students would not necessarily remember to do an energy balance on a control volume looking to solve for V2, but that's the approach that we used. It was conservation of energy to get the exiting kinetic energy so that we could then calculate the exiting speed. They would typically use or want to use conservation of mass principles, but it'll be a dead end. Okay, also just to point out, did we ever use P1? Was it ever used in this problem? It really isn't. But you say P1 can't be any random number. It has to, well, when we get to the second law of thermodynamics, we'll find that there are limits on what P1 has to be such that this system doesn't have some sort of property known as entropy being destroyed. It can only be generated. So it can only have irreversibilities. At the best, it would be reversible, and meaning there would be no entropy generation. But in reality, it's going to have some friction, some irreversibilities. And so that's probably a little bit of a thing where at this point you're saying, how come we never used P1? And isn't it important? Well, it is important, but it's important when we get to chapter 6 and entropy. All right, with that, we're done with this problem.